Thank you, Andy, and thank you to Valley Space for hosting this. And I'm sorry once again that Ollie, who I've worked with for a really long time, couldn't make it here today. The talk that I'm going to give today has a slightly different flavor, and it's based, so far we've been talking a lot about products and perhaps products that make products, but one of the important things that I've heard a couple of times being mentioned is technologies, right? How do we bring those technologies into the products that we want to work on? And why does this matter? Well, if we're designing the airplane of the future, for example, how do we figure out what we're going to put in there? We need to ask a bit the reverse question, right? How do we find the right technologies to fit the products? And this can lead into real results. So for example, here, the Zero-E program is going to have a flight demonstrator for hydrogen propulsion, which is a very exciting new idea. OneWeb satellites using electrical spacecraft propulsion. That's, again, a question about technology and using the right technology that had to be developed in the first place. So this question started based on, actually, Olivier's experience back when he was working on road mapping and technology development at Airbus, was essentially, well, we want to figure out which technologies we're going to work with in the future. And we want to figure out where are we going to allocate our investments when it comes to technologies. And how can we actually go about asking that from a technical perspective? So back in 2017, we essentially asked, how do we do with this modeling, but a modeling that is inherently parametric, cloud-based, easy to learn, where you can keep track of version control. And most of you, since we're all here, probably know the answer. So Valley Space was actually picked as a tool for working on this. And a couple of trials were used, and it was put into phase at Airbus for doing multiple concurrent facility design studies. So the modeling technologies is something that we can actually do using tools like Valley Space, but why should we care about modeling technologies in the first place? The key idea is that the way people have often thought about technologies are technologies as standalone entities. Okay, we need to develop, I don't know, hydrogen engines, or we need to develop this other tech. But it really matters the context where they're developed. And we need to think from a systems perspective where that technology fits into the product strategy of whichever company you are. You cannot just think, I'm going to invest into cryptocurrencies because it's cool. Or perhaps you can, but from a product perspective, you want to understand why does it add value. So that's why we need to understand this in the context of a host system. The simplest way to do this, and that's the way I will present today, is to do a two-level decomposition where we have the product on the first level and the constituent technologies on the level underneath, and we're constantly understanding the dependencies between the technologies and the main product. So once this decomposition has been done, we can then perform system modeling to help us answer these questions, such as how do I pick how much I want to invest or push into a certain technology? How much value is that going to bring back to the product that I have? So, and for this, we're going to use the tool of sensitivity analysis to actually understand exactly this linking between what I want, what am I getting out from this for the future of the product that I'm going to develop. So, as an example, here is a model, and I don't expect you to read the details of it, and I'll walk a little bit more into the exact components of it, of a long-range aircraft. So for example, Boeing 747, where we need to think about what are the key functions that we want to deliver and what are the figures of merit. And that actually brings me into the modeling blocks that we need for this, key elements of a system model. So first, we need to think about what are the main processes that our product need to carry out to create value? Then what are the major enablers that will give us this function? And here is where the modeling key part comes in, which is understanding what are the parameters that my modeling is going to be operating under, and which are the design variables, the variables that I can actually control to design what I want to work on. Dependent variables, which are the variables that depend on the design variables and the models that I will have for those. And this is the key part of all of this, is having figures of merits that are relevant for the product that you're developing. So here's an example of a system decomposition taking, for example, a flight mission, and we have a set of 3 figures of merit: reliability, range times passenger, and cash up operational cost. These are the things that we care about at the flight level. And we have a set of different products in our portfolio that we can use to achieve those flight missions. So now, if you're the technology road mapping person within your company, instead of thinking, which are the cool techs that I see on the market, and just saying, okay, we'll just invest X amount into it depending on how cool I think they are, we think instead, okay, so how much added value in terms of figure of merit that this particular technology give me? So for example, if I have a certain aircraft and I want to invest, or I want to get 10% better payload mass, what does that mean in terms of what do I get for reliability, for range passenger, for cash operational cost? Now, of course, there can be commonality even between the products, so you need to take that into account too. And a really good tool for that is the science structure matrix. So this is a matrix that captures the dependencies between both the products, the fact that you can have commonality and dependencies between the products, and the technologies. The fact that the technologies that you're working on, changing one technology is going to have an impact on multiple other technologies that you're working on. So for example, you might think, oh, we just want better engines. Well, now it turns out that for aircraft, if you want better engines, the engines will be larger. And now if you have larger engines, that's all of a sudden going to come back to you as a ripple effect in terms of larger structural loads. So now you need to think about those ripple effects and accounting for those. So all of a sudden, just asking the question of which technology do I want and how much do I invest to it becomes how much does the technologies that I would develop to improve that impact other technologies. So why do we need this process that I was just describing? Well, once we can break down a system into figures of merit and actually have models that capture them, we get a solid basis as opposed to just feelings basis for making an argument for which technologies to invest in. But further on, we can benchmark different choices of technologies, investments, and products against one another. We can examine which other missions a product could be used for. And most importantly, we can make decisions on how to set the right targets for the technologies that we're going to invest in. And of course, on top of that, we can build an R&D portfolio for the company. So to walk you a bit through an example of the ideas I've discussed so far, let's take a 747, 400 aircraft. This is an aircraft that was first in flight in 1988, so it goes a long way back, actually. And at the time of construction, it's a large aircraft which has about 416 passenger capacity at its maximum, and has a range, oops, I don't have it here, but anyways, we'll get to it on the next slide. And has a specific set of figures of merit that you can see here on the left side that reflect the technologies at the time of when it was built. So, oh, that's where it is. It has a range of 14,000 kilometers. So, by the way, if some of you are wondering, well, this seems like an old airplane, it's still flying, and this is from a flight that Olivier took at some point in July, so it's still fully operational, Boston, Frankfurt. So this is a flight that, let's say that what we can do today with the current technology of the airplane, we can do, for example, London Heathrow, LAX. Now, perhaps we want to change the mission route to do something longer. So let's say we change it to doing Singapore to New York. Now, the range, as you can see on the very bottom, is a bit longer than the 14,000 kilometer we were just talking about earlier, the range of the Boeing 747. So currently, that's not a feasible mission for the Boeing 747. So what if we were working with the Boeing 747 and we wanted to improve it? What are the set of technologies we could invest in for achieving such a flight range? Well, we could train passengers for fuel. So you just put less passengers in the airplane, you can fly longer. We can improve the engine technology. We can develop lighter structures. We can, of course, improve the aerodynamics by doing further tests, developing the either the structure of the airplane or the wings. So if we wanted to test either of those options, here are the numbers for what you would actually need to do based on the range equation, Breguet range equation, for those of you that are familiar with aerodynamics. So we could replace 106 passengers with fuel, meaning that's less income for the company that's flying this. We could improve engines by 8%. We could reduce the empty mass of the aircraft, meaning somehow try to remove structure from the airplane, which might not be compliant with regulations. Or we could improve wings by about 8%. But these are the type of trade-offs that we want to get to, that we want to develop, so that now that we're thinking, well, this is where we want to go. Now, what are the trade-offs that we want to make? And we could, of course, do any combinations of the above. But of course, perhaps doing the 8% improvement of technology in engines is a lot harder than doing the 8% improvement of technology for the aerodynamics. So that's where understanding this at the higher level, you can take it to the next level and iterate. I'm just showing the example at 2 levels here. So the underlying assumption is that when we're working with these designs, they're the result of some sort of optimization. So the design points that we saw about the Boeing 747, we could assume that it's, well, it's probably suboptimal, but we can assume that the designers try to make it optimal. And we could see it as the result of some optimization, which can, in sort of abstract terms, be put as a minimization of an objective function, subject to, as a basis of some design variables, subject to set of inequality constraints, equality constraints, and subject to some bounds on X. Now, what we care about were the objective functions. That's what we want to minimize, right? Or maximize, depending on what we are interested in. And to understand, so we're going from the point, right? We started with the 747-400, and we want to understand, well, how can we improve that? So I'm just going to walk you through kind of the process that we did previously. What essentially we're carrying out, and what we did previously, is what we call a sensitivity analysis. We want to understand how much does the thing that we care about, the range of the airplane, change as we adapt the different design variables, which become the technologies in our design. So we want to understand the effect of changing the design variables. We want to understand the change of changing the parameters, or even changing the constraints, because we somehow can change the operational constraints because we develop new materials. So obviously the simplest approach to this is just doing it through partial derivatives and developing sensitivity through mathematical methods, essentially. So there are a set of different mathematical methods that we can do for answering this question. And on the right-hand side, you can just see the range equation, the Berger range equation, which tells you how long range you have for an aircraft, given value for certain specific parameters on the steady state velocity, the L/D factor, the specific fuel consumption of the aircraft, and the initial and the final weight of the aircraft. And the way that we can get the sensitivities when we do have such analytical expressions is just by applying some mathematical operations that you can see further on. And this way we can, of course, get the sensitivities with respect to the different technological parameters that we care about. So the lift to drag, for example, it's an aerodynamics related parameter. The SFC is related to the engines and the performance of the engines. The final weight, you can say it's an accumulated factor, but that's structures goes in there. Number of people you put on the airplane goes in there, and so on. So, but we cannot just look at the sensitivities as a standalone calculation. It can sometimes be really useful to also normalize the effect to understand it in terms of percentages. So here we go from brute numbers in, brute numbers out. So number of, so L/D number in and range out. Instead, we go for percentage in and percentage out. And this can help us get a better understanding just from a normalized perspective. Well, if I want 10% improvement in performance, how much would I need to improve these technologies that I rely on? By how much? By 1%, by 10%? And just as some interesting rough numbers, turns out that, let's say, hardware technologies, depending where you look, develop between 1% and 5%, and information-related technologies, well, per year, develop actually at a much faster rate, up to 40, 50%. So there is also another element. We talked about the constraints, and obviously understanding, since we're doing system optimization in the first place, we can also recover an understanding of how sensitive we are to the constraints. So for example, the material properties might be constraints in the design that we have by taking advantage of something that we call Lagrange multipliers when we're doing optimization. So far, kind of the overarching argument has been we want to understand which technologies we're going to invest in by looking at key figures of merit that belong to those technologies that are part of my product, and then finding sensitivities. So I'm just going to walk you through some examples that relate to this idea from practice. And the first one has to do with single stage to orbit. So most of you are probably familiar with multiple stages to orbit because that's how it's done nowadays. And that's how all the rocket companies do it. Back for a while, the idea of having a single stage to orbit, essentially an airplane to orbit. By the way, some of you might think of the space shuttle as being the solution to this, but the space shuttle did sort of drop the main tanks and just go on its own after a while, so that's not a single stage to orbit. But imagine a space shuttle, but without all the tanks that were going on and the side rocket boosters that you had in the beginning. That's the single stage to orbit concept, essentially. And NASA actually invested some serious amount of money into this. And one of the challenges, of course, when you're doing these things is that the physics are always against you. So we can go back to the rocket equation, which you see on the bottom here, which tells you as a function of some mass properties of your spacecraft, how far can you get into space? That's what delta V means, essentially. It's how far into space can I get? And even to get into space, there's some minimum requirement of delta V. So that's a key sort of parameter. And the target for this technology demonstrator program, which was done by Skunk Works and Lockheed Martin, it was the X-33 demonstrator, was to have 130 kilograms with a mass fraction of 0.1, which is a pretty aggressive number. It would operate on liquid hydrogen and oxygen with a really high impulse-specific coefficient of 440 seconds, which is like high. So basically, they were making assumptions on their technologies that we could achieve the single stage to orbit if only we pushed for these ambitious goals. Now, the project was canceled by NASA after about 1,000 million were spent in R&D on this project. This is, of course, a rendering. No airplane ever, or no single stage to orbit flew, even though I think they made some smaller prototypes, small-scale prototypes. So how could they have figured this out by just stepping a bit further back? Well, and what was actually the original problem? Well, it goes back to the rocket equation that we saw on the previous slide, and that has been slightly rearranged here, that has to do with the relationship with the delta V that you need to even get into space and the structural ratio, which was the technology that they wanted to bet on for achieving this. So actually, it turns out that if we draw a graph that shows as a function of the mass fraction, how much delta V I get, how far do I get into space, depending on the mass fraction, just taking this equation, we can see that if we set in 0.1 as the structural mass target, I end up only getting about 10.5 delta V. Now, to leave or to go into low Earth orbit, which is kind of your minimum requirements for getting into space and staying there, you would need about 11.5 kilometers per second. And that's the unit of how much it costs to get you there. And to actually do that in the first place, you can only do it if you have, based on these equations, a structural mass of 7.5%. So just from the get-go, you could say that the technology was, or the investment in R&D was a bit doomed based on the poor understanding, or perhaps being too ambitious on this structural factor and how well they would be able to do given the constraints on material properties of the day, because that's underlyingly what governs this factor. So that's one example. Another example, and this is actually a bit more based on my research, is not so much related to a particular technology, but it has to do just with, in general, we're talking earlier about the idea that, well, we want to understand how we're going to set targets for the technology. And for doing that, we developed these models, and we could think of these technology targets as input and sort of whatever you're achieving from your technology's outputs. But can we exchange these inputs and outputs? So, and does exchanging these inputs and outputs simplify the model somehow? And so that was actually the topic of my research, and I will not talk more about it, but I'm happy to spend all afternoon talking to you about it if you want afterwards. And this was a case study that we did on new technology that's also coming on board, which now the way we go to space, most people assume you need some form of fuel to get there, and big rocket, but there are other ways to get into space as well. And one of them is to get there by a high altitude balloon. And a couple of startups have already gotten this idea kicked off, actually, and are working on the right technologies for getting there. So here on the next slide, I'm just showing some, we saw earlier this matrix that describes the inputs and the outputs and the dependencies between the different technologies. Here, actually, it's the dependencies between the calculations. And on the left-hand side, actually, although there are not many dots, the ones that are off the diagonal indicate that we have some cyclicity, and by just exchanging the inputs and the outputs of the actual models, we can achieve a sort of feed forward, which is this very nice triangular matrix that you see on the right-hand side. And that's just one of the methods that we can use to further actually implement this modeling that I was just talking about. Now I'll go to a different example that's coming a bit back with our feet on the ground that has to do with, again, setting these targets for technology and how to figure out what are the right targets for technology. So one of them projects that we did in the lab a couple of years ago was on the concept of instead of getting to the moon and just bringing everything along with you and coming back, how about you produce the fuel that you need for the road, and you kind of have depots and you refuel, and that way you have to bring less stuff with you. And this concept is normally referred to as in situ resource utilization, so ISRU. And here you can see a network of different points in space. Some on the moon, so the green dot is on the moon, the red dot is on Mars, the blue ones are on Earth, and the yellow ones and pink ones are in space. And this is a network between these different points. And the red arrow shows you sort of where the astronauts would go, and the sort of orangey ones show where different cargo modules would go. And basically the problem that we wanted to understand is, well, how can we reduce the amount of total mass that we need to bring to LEO in the first place? Because that's the stuff you have to take off from Earth, and that's very costly, right? So, by the way, this is just kind of some illustration of you would have some production on the moon, some production on, on Mars of fuel, and then you would bring it up to space to do some refueling. So, and this is a graph showing sort of an understanding of that picture. So if you look at the black curve, you can look at the total mass to LEO. So we want to bring that down ideally, but what do we pay in exchange? We pay in exchange creating infrastructures on the moon, the Mars, so that's the amount of kilograms that we need to send are the red bars to Mars and the green bars. And this is an entire network optimization actually of this. And that's where you got these weird jagged lines from. And the key idea here is that, well, if somebody were to just tell you, okay, we're gonna go send humans to Mars, come back, and we're just gonna put stuff on the moon, you know, because I think it's a great idea, so let's invest in technologies for producing resources on the moon. Well, in reality, turns out that it doesn't really make sense until you have a minimum production rate of resources on the moon. So that means that you need to develop the technology that can actually give you that rate. Otherwise, if you develop something that does less than that, you sort of threw your money into something that was not very useful. So to bring it all back in, we need to think about technologies not as just standalone things that are cool and have a coolness factor and we've heard of buzzwords and so on. We need to think of them how they fit into the product or the system that we're working on. The sensitivity analysis help us quantify how much a certain change in technology can drive a certain change in product performance. And we can use this through mathematical tools like partial derivatives and normalized. And this can also help us, of course, set targets. And ultimately, to bring it back to the very beginning, these models cannot just live on one person's desk. They need to be shared. They need to be part of a bigger team working together. And that's why we need the type of technologies that Valley Space enables so that people can work on modeling for technology development together in the future. So thank you very much, and if you have any questions, I'll take them.
Thank you very much, Johannes. I think you did an excellent job as stand-in there. And for somebody that was reading somebody else's notes and presentation, wow. Okay, let's open up the floor to some questions if there are any.
I'm always impressed by these mathematical equations. And the challenge is a lot of times you don't know what you should be doing the equations to until you're 6 months or a year into the development cycle. What are your thoughts on how you bring those math models in earlier?
Great question, by the way, and I think about that too, actually, quite often. I think there's different levels of modeling that happens over the stage of any product, right? And but sometimes it's not only about bringing equations in and you solve the problem, because you can end up in this garbage in, garbage out problem where, you know, are you really capturing the right models in the first place? So I think some equations are more useful than others. I don't know if that's like the right way to put it. And so, for example, here in the presentation that I showed today, when it was the simple equations, somehow people have developed a very good, I guess, relationship to predict the range of an aircraft. And that's something you can start with on from the very beginning, and you don't need to do some deep modeling with it. And so I think these type of relationships are really useful. And I guess they're more domain specific and they rely on expertise within the domain. Sometimes people have developed empirical models over the time of a company, kind of to either for some simplified cost models. So I think these, if you have them or if you know about them and you don't have to spend a lot of time developing them, definitely from the beginning. But sometimes you don't need equations, and sometimes having more something like a behavioral model that just shows you kind of the different states and transitions between states that your system is going to go into is something useful enough. But then if you're all of a sudden going to particle physics or something else, you need to go down to the differential equations. You need to understand these things. So I think it's not an obvious thing to know. But I think if within your domain there are these rules of thumb equations, I think those you should use from the very beginning.
I know it's an extensive topic, but could you elaborate a little bit more on the usage of restructuring the DSM for the conceptual stage? I saw that you had the restructuring, yes, but didn't go into details.
One of the things that actually happens when you use these simpler models and you're not, let's call it, doing differential equation modeling, which in my mind is kind of, it's not the most advanced you can do, but it does take a bit of knowledge to get there, is that you end up with a set of input-output causality understanding between things, and you can end up with loops between your relationships. And so part of the research work behind the restructuring was figuring out ways in which we can restructure actually the equations to make it easier and to actually remove the loops that you have in the problem while still resulting in the same output. So we can talk more about it afterwards if you want, and I'm happy to share my thesis with you too if you're interested. But the key takeaway is that these are ways in which you can, sometimes you just have like 3 or 4 equations, so it's not that necessary. But when you have large set of equations, the type of loops that you can end up having can cause some calculation problems, and these are ways of solving that essentially. So thank you for your question.
We've talked a few times over this conference also about what's coming next and AI, and I see oftentimes people using the word AI for I want magical outputs and something in between happens that I don't understand. Optimization in engineering is oftentimes also that, right? Like it's a bit of a black box, and you hope that what comes out is right. And it probably is also similar to AI in engineering, that it's not being used very much. We talk about optimization in engineering, but often it's just an engineer trying to get a good gut feeling with a spreadsheet and taking the best option. what do you think comes next in engineering? Do you think bringing optimization more to the masses is gonna bring us the results that some people hope for AI? Or are we gonna jump that and just get models that we completely don't understand and they're gonna predict better maybe even than explicitly written down optimizations, our designs of the future?
Well, I hope we fall into the first category. But I think one of the things, and this is one of the research areas that I'm particularly interested in, and I think as in academia we've not done a good enough work on it, is kind of the designing the user interface around optimization. So there are a bunch of things that can go wrong when you try to optimize things and you put in models into an optimizer. And for most people that deal with that, if you're just using, I don't know, a regular tool, you just see some strange error that you have no idea what it means, and then you just change parameters and hope that it somehow fixes itself. And I think because sometimes the problem is not even the method that you're using for solving the optimization, it's actually that the formulation that you're giving to the optimization problem is incorrect or has some assumptions underlyingly that just doesn't make the problem solvable in the first place. And so I think if we can work on research that helps the user better understand, oh, you forgot a constraint here. This cannot be solved because there's clearly a constraint missing. If you add a constraint on this variable, all of a sudden I can solve it for you. Or you have provided too many constraints, but you can take this one, and all of a sudden it will work, you know? Or so giving more of this so that people get more comfortable with not seeing just red boxes popping up and closing their eyes and running away and then just telling somebody else to do it and trust their results. I think that sort of exchange between the person and the optimization will help address what you're talking about. When it comes to AI, I know that they're trying to work on explainable AI and these other concepts of better understanding what's happening inside the AI. So perhaps that's a similar theme, but I don't have as much expertise in the domain of AI. Thank you for the question, Marco.
Excellent presentation. In full disclosure, I was the X-33 program manager for Boeing, and we elected not to compete further because we felt the problem was over-constrained. If we wanted to get the mass to orbit that NASA wished for us to get to orbit, the vehicle grew enormously, predominantly because of the cube square law, and it became impractical to build. So I think your conclusion on that was correct. The question is, how would NASA or any other entity choosing to do something as challenging as that use the mathematical formulation or techniques to say, is it time for this technology? Can we make this work? Or where should we invest our money to improve that variable which is the most sensitive to the performance of the final system?
Yeah, thank you for that question. And I realized that obviously in the way that I painted a picture, I put kind of NASA a bit in a big picture and made it sound like it was obvious from the beginning, right? And that's not at all the case. And I mean, NASA is amongst the smartest people out there, and Lockheed Martin and the contractors that they had on it too. So I think the reality is that sometimes we don't have the right models yet, right? And so just saying that the answer is modeling might have been cheating a bit to you guys and saying, if you do have the models, then, and they do exist, right? Don't pretend they don't exist for many use cases. But very often, especially when you're jumping onto doing something that is so novel that, and even the technologies that you want to bring in, many of them are novel, and you don't have the right models quite yet, you know, at that point, modeling is not yet the answer, right? Then there would be some iterative process, other methodologies, and then I guess the result, and that's why we have people like NASA doing this, is because it's a risk, right? And we learn from it, and then the important thing is when we have learned from it to make those models available or bring them in so that people in the future can potentially use it for their strategies. At least that's how I think about it.
Johannes, I think that's all we have time for, but thank you for the brilliant answers, and I'm pretty sure you'll be getting some people asking for some more explanations during the coffee break. So thank you so much. Big round of applause for Johannes.